Good morning, guys. So let's start today's class. Today we will be revising a little bit about the dehydrohallucination part. I'll just briefly write everything at one place, so that it will be easy for us. And then we will start dehydration of alcohols, the same preparation of alkenes. Instead of removing hydrogen and halogen, we will be removing OH group and hydrogen. So dehydration, removal of water molecule. So from alcohols, we will be performing this particular reaction. So before we go over there, we will just quickly revise regarding the hydrohallucination of alcohols a bit, and then we will move on to dehydration part. When it comes to dehydration part, the rearrangement is a bit important, so we have to concentrate more on that. So quickly I'll revise regarding dehydrohalogenation, or else you can take this down everything instead of revision. So take preparation of alkenes. The first method will be dehydrohalogenation. I'll be giving a statement. Dehydrohalogenation of alkenes. Okay. So take down the statement. Alkyl halides. Alkyl halides. Hmm, alright. So alkyl halides on dehydrohalogenation. That is, one second. Alkyl halides on dehydrohalogenation. That is, removal of hydrogen and halogen atom from adjacent carbon atoms. From adjacent carbon atoms. In the sense, we are eliminating carbon and hydrogen from alpha beta carbon, right? So this can also be called as beta elimination. The same UN-E2 mechanisms only, elimination reaction only. Here we are specifically removing the groups or atoms from adjacent carbon atoms. So alpha beta. So that's why specifically we call it as beta elimination. Gives us alkenes. Gives us alkenes. So if we take the general reaction, R, H, X, H, 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 and H. So by following beta elimination, this is our alpha carbon and this is our beta carbon. We are going to remove hydrogen from beta carbon and halogen from the alpha carbon. So that we end up having carbon-carbon double bond. So we have R, H, H, and H. Just a simple reaction. So we are doing beta elimination. So we are removing hydrogen as H plus and halogen as X minus. So that we will have a carbon-carbon new pi bond form, giving us an alkene. So this is an alkyl halide, and we are ending up with alkene. We are ending up with alkene. And in what presence, in presence of what molecule does this dehydrohallucination happen? So dehydrohallucination happens in presence of base. In presence of a base. Depending upon what type of base it is and what is the concentration of the base will determine the type of mechanism. Otherwise, we start with alkyl halide and we end up having alkene. Are you revising again? Yes, I am revising again so that everything regarding dehydrohalogenation will be at one place. Only few minutes, nothing more than that. So please take down the bases. What are the bases that can be used? Yesterday I shared in the group one sheet, right? In that Specific bases in favor of even mechanism, E2 mechanism, even CB mechanism are listed in that table. So in general, you take down some important bases regarding the exam. Exam and all, you don't need to take down that sheet, that all bases, those all bases, right? So just simply note down the common bases that you see while writing this alkyl halide to alkene conversion. So the first one is alcoholic hydroxides of alkali metals. For example, alcoholic NaOH. This is also base, right? Or else alcoholic KOH, or else alcoholic cesium hydroxide. So we can directly use hydroxides as our basis, or else we can use amides also in liquid ammonia, that is NaNH2 amines. So in liquid ammonia, or same KNH2 in liquid ammonia. I'm just giving you the common combinations for the bases because we have never concentrated on the bases. So just take them down a list. So in liquid ammonia. So alcohols, alkyl amines. Then you have alkali metal alkoxide ions actually in presence of alcohols. So CH3 O minus Na plus. So this is methanoxide, sodium methanoxide in methanol CH3OH. Instead of sodium methanoxide, you can even take sodium potassium K plus actually. So same type of alcohol should be used. Whatever is your base, above statement, yes, mine scroll down here. One second. All right. So either normal hydroxide or metallamines NaNH2, KNH2, or methanoxide, sodium methanoxide, alkoxide ions in their corresponding alcohols. So these three combinations are the most commonly used bases to perform this dehydrohalogenation. The strength of it, the concentration of it will further determine what is the type of mechanism it will have. Otherwise, it's just the same. Alkyl halide along with the base, beta elimination will happen and it will give us alkene. Simple. Okay. So next. Yes. So this is one set of combination. You can even use ethanoxide. You can use ethanoxide. C2H5O minus Na plus, or else C2H5O minus K plus in ethanol only. So your alkyl part and your alcohol should be same carbon number. So that will be there. Alcohols. Okay, so and one more you have a different one, trialkyl amine R3N. Trialkyl amine R3N. So if you take a simple example, that triethyl amine. So any one of these four combinations can be used to perform this dehydrohalogenation. And what do we have the ease of halogenation when it comes to alkyl halides? Tertiary alkyl halides are more reactive than secondary than primary. So that is one thing, the order of reactivity. This is common. Why? Because the type of carbocation formed will be more stable, then only you'll have a proper product. So tertiary carbocation will be more stable than secondary than primary. So when it comes to the leaving group, that is X minus, iodides can be easily removed than bromides. than chlorides, than fluorides. So fluoride is the poor leaving group. Here I am not giving exceptions. I am generalizing all the mechanisms. Okay. So that is one thing. And what is the type of alkene that we will end up? So when we talk about alkene, our final product will always be a stable one. That is simply most substituted one. What happened? One second. What did I wrote after KOH? CSOH, na? Alcoholic ALC, alcoholic KOH slash ALC, CSOH, cesium hydroxide. Mm, First point, yes, it's cesium hydroxide. Okay, all right. So, all right. So when it comes to even mechanism, everything even or E2, it entirely depends upon the base. So if the reaction proceeds through even mechanism, only low concentration of you require low concentration of weak base. Here temperature is not that factor. Even at room temperature also, the reaction will move forward. Here everything is dependent on the stability of the carbocation, because that is our reaction intermediate. So everything is about the stability of the carbocation formed. And now when it comes to E2, here we require high concentrations of strong base, then only the beta elimination will happen. And this requires some heating, some high temperature, because the rate was directly proportional to temperature when it comes to the E2 mechanism, and it happens relatively higher temperatures when compared to the room temperature. So this is everything about dehydrohallucination. uh, Third point, yes, sorry, I'll show one second here. uh, Wait, I'll wait a minute. You finish this writing down, then I can move forward. Every time you have to scroll up and down. All right. So 3 and 4. Mm. I'll wait a second, ma. You please note down, and from there we'll continue. Is it true that tertiary alkyl halides prefer to undergo even elimination? Yes, it is true. When it comes to tertiary alkyl halide, the type of carbocation formed will be a tertiary, right? And it is the most stable than the other two types of carbocations you end up with. So mostly for tertiary alkyl halides, the preference will be for uh, even mechanism only. But it can also undergo E2 mechanism depending upon the strength of the base we are taking. Yes, definitely E1 is most favored by tertiary alcohols because of the most stable intermediate formed, that is tertiary carbocation. Yes, all right. So these are whatever the examples we have seen till now, they are just open chain compounds. We haven't touched any cyclic compounds at all, cyclic alkanes, cyclic haloalkanes. So we will see a simple example, and from there we will start dehydrohalogenation. So very simple, bromo 1 comma 1, sorry, Br group you have, and you have CH3. So same here also, you have, this is also a haloalkane, right? But instead of being aliphatic open chain, it's just a closed chain hydrocarbon. In this one, let's see what are all the possibilities for us to have an alkene. So at what positions we can perform the beta elimination part, and from there let's try to see the major product. So you have bromine group and methyl group at the same position. Now this is your alpha carbon, right? Because you have bromine substituted. So this will be our alpha carbon, and this will be our beta one, because this is also adjacent, first adjacent, and this is also our beta carbon. And how many beta carbons are there over here? 1 and 2. So there are two possibilities for the removal of halogen and hydrogen in this example. So let's see those possibilities. So let's say initially the dehydrohalogenation, the removal of hydrogen, happens from beta 1, which means the methyl group substituted on the cyclohexane ring. So what do we have? Bromine will be eliminated and one hydrogen will be eliminated. So between the alpha carbon and the beta carbon, a new carbon-carbon double bond will be formed. So that is one possibility. Now in the second possibility, where the hydrogen is eliminated from the beta 2 carbon, that is a new pi bond will form over here, and you have a methyl group as a substituent. So between the product 1 and product 2, which can be assumed as the major product according to the Sadzeff rule? Any idea? 1 or 2? Which is more substituted, 1 or 2? Obviously, product number 2 will be the major product, because it is the most substituted alkene. This is most substituted alkene. So this is gonna be our major product. Without any doubt, this is gonna be our major product. It depends on base also, right? Everything is about elimination of hydrogen and halogen. What mechanism it is taking, by what mechanism the reaction moves forward depends on the base. End of the day, only two possible products are there, right? This is our alpha carbon, and this is our beta 1 and beta 2 carbons. Between these two carbons only there has to be an elimination. There is no doubt in that. Only thing is, through what mechanism the reaction moves forward depends on the base. That's it. But the products remain the same. The type of base, if at all, if there is any steric hindrance from the substrate or the base, probably we can encounter a different one. Other than that, these two are going to be our major products. Okay. So this is cyclic haloalkane. So even here also, I meant if there is a bulky base, first one is major product. Definitely, if there is a bulky base, definitely that's what. If there is a bulky base, definitely the major product will change. Here we are not, they didn't give any base, right? So let's take a simple one only. Some OH minus. That's it. Clear, right? Definitely, bulky base will have its effect on the major product. Here, no such bulky base is there. As usual, any one of the beta elimination can happen. So either it least substituted alkene or most substituted alkene. Most of the cases, the major product will be the most substituted alkene, except in case of those exceptions are not. Okay, so what type of haloalkane, cyclic haloalkane this is a tertiary haloalkane. Why? Because the bromine, whatever the carbon, alpha carbon you take especially, is attached, the bromine is attached to three other carbon atoms. In the sense, not sorry, not no, it's not tertiary. So bromine we have, and the alpha carbon, whatever we have, we will end up having a tertiary carbocation, right? If you write the previous step. So this is one carbon, this is another carbon you have, and you have CH3. So the positive charge will end up having on a tertiary carbocation. So this is a tertiary alkyl halide, alkyl halide. Now, just like in open chain compounds, even in cyclic compounds also, we have the same order. Tertiary is more reactive than secondary than primary. So just now we have seen the tertiary example. So three carbons, 1, 2, and 3. So this is tertiary alkyl halide. If you take secondary alkyl halide, you'll have something like this: CH, Br, and CH3. It is attached to two other carbon atoms. And greater than, primary means a straight chain kind of, CH2, CH2, Br. So this will give us tertiary carbocation, this will give us secondary carbocation, and this will give us primary carbocation as our reaction intermediate. The same reaction order, just like open chain compounds, here also we will be having for cyclic alkyl halides also. Right. So this is about dehydrohalogenation. So the important thing is between what carbon atoms the elimination will happen, what is the major product, and are there any exceptions possible for the given base and all. So that is important part. So OH minus is a strong base, right? Shouldn't it undergo E2 mechanism? Probably it will go mark, but the thing is, definitely it is a strong base. We are not denying, right? It can undergo, but here we did not mention any concentration. In what concentration we are taking, right? Most of the cases, even if it undergoes E2 mechanism also, we will be having more substituted alkene only as the major product. Yes or no? The only point where base is given much importance is to determine the mechanism. Otherwise, the type of product formed will always be mostly 90% SADZF, major most substituted alkene only. Mechanism and all will depends upon the strength of the base. All right, and the concentration that we have taken. Okay. So this is about dehydrohalogenation. Now let's see dehydration part. This part is important, and when it comes to mechanism, we are going to see a slight deviations. So there is gonna be a little bit arrangement and all happening to get a stable carbocation. All this process we will see. So take down the second preparation method, dehydration. And to what molecules we are performing this dehydration? We are going to be doing this dehydration for alcohols. So dehydration is nothing but removal or elimination of water molecule, of water molecule. And in alcohols we have ROH, right? Alcohol, let's take, you have hydrogen, hydrogen, and hydrogen, OH, and H, something like that. I'm just taking an alcohol. So here, this is our alpha carbon because our substituent present, the most preferential substituent will all, to whatever carbon is present, it's gonna be alpha. So this is our beta carbon. So here also elimination between adjacent carbon atoms only, but the eliminated molecule will be different. We will be removing water molecule H and OH from adjacent carbons are removed as H2O, and the remaining part will form a carbon-carbon double bond, H, H, R, and H. So this is alkene and this is alcohol. We ended up having alcohol by the removal of water molecule. Now, whatever the agents, we require a reagent, right? Our reagents will be dehydrating agents. Our reagents will be dehydrating agents. Either we can take acids or some other different types of oxides also we will take. Mostly acidic oxides we will be taking. So we are going to use dehydrating agents to remove water molecule, to remove water molecule from our reactant. So please take down the statement for this. By the elimination of water molecules, H2O, using dehydrating agents, and alcohol is converted into an alcohol is converted into an alkene. So this is just simple statement. So this is the statement, this is the model reaction, right? So now we will try to see what are the specific dehydrating agent. Here also I'll give you that list, the most commonly used ones, and then we will see the actual mechanism using these examples, and what are there any exceptions involved also we will try to see. So when it comes to dehydrating agent, the most commonly used one is concentrated H2SO4 at higher temperatures. So mostly we will be using in the range of 443 to 453 Kelvin. So mostly you will be come across in concentrated H2SO4 or concentrated phosphoric acid H3PO4 at the rate some 470 Kelvin. So these are the two common reagents that they will give on their arrow. So they are just strong acids which will help in the removal of these water molecule. They are good dehydrating agent. Or else another common alumina Al2O3 at 663 Kelvin. So this is also very common, and there is a certain importance to this alumina Al2O3 that I will tell when we are writing common examples. So Al2O3 at 663 Kelvin. This is also one of the dehydrating agents. Next, fourth one. We can have P2O5 heating with P2O5 or P4O10 or P4O10, or else you can take dry HCl, or else you can take a mixture of KHSO4 and dehydrating agent CaCl2. So these are some commonly encountered dehydrating agents. So mostly 1, 2, 3 will appear in most of our reactions. That too, concentrated H2SO4 and Al2O3. This H3PO4 you will see for cyclic compounds. Okay, so please take this down. We will see certain examples, and from there we will see the mechanism. Here also the same rules apply. Most substituted alkene will be the stable alkene. So most of the times we will be looking at the product, that is major product, to be a most substituted alkene, that is SAFE product. But there are some deviations also, but not in the type of major product form, but how is it formed will be a little bit interesting in this particular dehydration part, we will see. All right, can we move on, or do we need a minute or so? Yes, let's continue. So let's see certain examples, and from there we will see the mechanism and all. Same even E2 mechanisms we will see, but a slight difference in the type of product form. So take down some examples. So let's start with simple one. CH3 CH2OH. So this is ethanol. So this is our alpha carbon and this is our beta carbon. Obviously, there is no other way for us to write the product. So we will be having ethene, CH2 double bond CH2 by the removal of water molecule. So we end up having ethene or acetylene or ethylene. So only two carbons, alpha and beta are there. So directly we have removed it. So let's increase the carbon number, CH3, CH2, CH2, OH. So this is Propane 1-ol, same, heating in presence of concentrated H2SO4, we will get, this is alpha carbon and this is our beta carbon. So from alpha you will be removed OH, and for beta carbon we will be removing one hydrogen. So CH3, CH double bond, CH2. So we got prop 1-ene by the removal of water molecule. From prop 1-ol we will be getting prop 1-ene. Now if you take butane 1-ol, see this is a primary alcohol, right? Because the OH group is attached to the primary carbon atom. This is also a primary alcohol only because the OH group, whatever is attached, it is attached to a primary carbon atom. So this is a primary alcohol. So you have CH3, CH2, 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 OH. Okay. So this is our butane 1-ol. Butane 1-ol. So you have concentrated H2SO4 on heating. What do we expect here? This is our alpha carbon and this is our beta carbon, right? You will be having, expecting product will be CH3CH2. This is our beta carbon. Between that, CH double bond CH2. This is our expected product, that too in major amounts. But in reality, some speciality to this butane 1-ol. The product formed will be but2-ene, not but1-ene. CH3, CH double bond, CH2. So this is but1-ene and this is but2-ene. So this is the major product, not but1-ene. Obviously there is a more substituted alkene part that will satisfy, but the thing is this is not the beta carbon, right? This is not the beta carbon between which the carbon carbon double bond is. So here there is some rearrangement, there is some rearrangement happening that we will see when we are dealing with the mechanism. So when it comes to alcohols, you just make a note. So when it comes to dehydration of alcohols, rearrangement will takes place, rearrangement will take place in the intermediate part, in the intermediate, to give more stable carbocation, to give more stable carbocation, thereby more stable alkene. And we will see how exactly this rearrangement will happen. But as of now, let us try to write all sorts of alcohols and the possible products. So we just take this separately down. So butane 1-ol, the expected product will be but1-ene because this was our alpha carbon and this was our beta carbon. But in reality, we will end up with but2-ene even if the double bond is not formed between the beta carbon initially. And that reason will be the rearrangement in order to attain maximum stability for the reaction intermediate. How come this rearrangement will happen, from what to what this rearrangement will happen, I will let you know in a bit. So all these three are primary alcohols. We even have secondary alcohols also, CH3, CHOH, CHOH, CH3. As usual, this is our alpha carbon, beta carbon, and same concentrated H2SO4 while heating. Here the expected product will only come CH3, CH double bond CH, CH3. This will be our major product. Why? Because this is our more substituted alkene. Obviously, there is another possibility because this is beta 1, this is beta 2. You have one more beta 2 carbon. So if beta 2 carbon is involved in the elimination process, we can also have CH3, CH, CH double bond CH2. But this will be our minor product because this is not the most substituted alkene. So a number of possibilities are there, but the thing is the type of end product is determined by the stability of the intermediate. Mostly it will be a carbocation. And how come that carbocation forms? I will let you know in a bit. So this is what type of alcohol it is. This is the secondary carbon, right? Because the OH group is attached to a secondary carbon. So this is a secondary alcohol. This is a secondary alcohol. We can even have tertiary alcohols also. Okay, what is this name? Butane 2-ol, and we end up having but2ene as the major product and but1ene as our minor product as usual. Okay, next we can even have tertiary alcohol also. Same process will be there. So CH3, CH3, OH, and CH3. So this is tertiary alcohol, isopropyl, isopropanol. No, no, no. 2-methyl, 2, 2-methyl propane, 2-ol. So here also concentrated H2SO4 we are gonna heat it, and obviously we have two beta carbons, both are equivalent, so the only possible way we can end up having minus H2O, please note down over here and over here. So double bond CH2 and CH3. This is the only way. Even if you try to remove the hydrogen from here also, this will be our alcohol. So this will be our alkene. 1, 2, 3. So we'll have 2-methyl prop-1ene as our alkene, and water will be removed as usual. So these are the simple examples. So all sorts of alcohols, primary, secondary, and tertiary, just like alkyl halides, can undergo this dehydration part, and the ease of reactivity will also be the same, because we will be mostly deal mechanism in terms of E1, that is a formation of carbocation. So, and carbocation stability is tertiary greater than secondary greater than primary, right? So in the same way, the reactivity of alcohols will also be the same. Ease of reactivity means to undergo dehydration for alcohols will be tertiary greater than secondary greater than primary, without any doubt. And obviously the product formed will be most substituted alkene only majority of the times. Okay, so that is one thing. All right, now we will see mechanism, simple mechanism we will see. From there we will see an exception, especially butane 1-ol we have just noted down, right? And from there I will give a particular order regarding types of alcohols, both in open chain and closed chain. We will see. So I'll wait a minute, you note down. Once you are done, let me know, and from there we will continue. Okay, if you want me to scroll up down, let me know. Please take a minute, note these things down, and then we can move from there. Rearrangement. And note down here, mostly this rearrangement will happen in secondary and primary alcohols. That too, this rearrangement tendency is more for primary alcohols if there is a possibility to get a secondary or tertiary alkyl halide in the given molecule. Okay, this rearrangement and all will be seen only in secondary and primary alcohols. Done. In this case also will we have Sadzeff and Hoffman rules. Mostly for alcohols, Sadzeff product is the dominating product. As far as the reagents, the type of reagents we use and the substrate we use are concerned, mostly it will be Sadzeff product only. Even if there is a Hoffman product, it will not be the major one. Major product 99% in dehydration is Sadzeff product, that is the most substituted alkene only. All right, can we start mechanism? Yes, okay, let's start. So take down the side heading as mechanism and take the tertiary alcohol only as our initial reactant. Mechanism. So E2 is also possible, but right now I am dealing E1 reaction only, E1 mechanism only. E2 and all we will see later because this will be a little bit different. E2 will not be a typical E2 mechanism like we have seen in alkyl halides. So let's start with the tertiary alcohol. So CH3, 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 OH. So this will be treated in presence of an acid. Acid will be providing us H plus. I'm just writing the model mechanism. Step by step we will see in my next part. So CH2, CH3, CH3 and water molecule will be released. So if you take the step one will be the removal of OH or the formation of oxonium ion. Step one will be attack of H plus on alcohol, giving an oxonium ion. So what exactly is this oxonium ion? We will see. So what do we have? Our initial reactant, a tertiary alcohol, right? So in that tertiary alcohol, OH group is there. OH contains two lone pairs of electrons, right? So these two lone pairs of electrons will be attacked, or let's just say the H plus coming out of acid will be accepting this lone pair and forming a new bond with the oxygen in the alcohol itself. So CH3, CH3, CH3. So initially you have OH. So one lone pair will be intact. The another lone pair will be donated to the hydrogen and will be forming a new bond. Oxygen is losing its lone pair, right? So it ends up having a positive charge. So what happened here? Initially we have OH and in presence of acid, the H plus coming from the acid will be attacking the oxygen's lone pair and a new bond will be formed. In the process, oxygen ends up having a positive charge. Now this is our oxonium ion. Oxygen with a negative charge is oxonium ion. Now this is very unstable. Oxygen is a more electronegative atom, right? It cannot contain positive charge on it for a very long time. And that's the reason why in the second step, this oxonium ion will undergo removal. This water molecule will undergo reaction, and that will be by the removal of OH2O. So oxonium is converted to carbocation. So how come it is converted? Let's see. So this is our oxonium ion, right? Initially CH3, 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 OH, H, you have a lone pair, along with that a positive charge. So in this process, the water molecule is removed. How is it removed? You have a bond pair, carbon oxygen bond pair, right? This will be withdrawn by the oxygen atom. So the carbon especially the carbon attached to oxygen atom is losing its share of the bond pair. That's the reason why we end up having a carbocation, and in the process water will be removed. Now this is our rate determining step. This is a slow step and this is our rate determining step. Formation of cation is our rate determining step. Why are we considering a positive charge on oxygen atom? It is just sharing its lone pair to form a bond with hydrogen. It is donating both the electrons required for the bond rate. Balancing of charge should be there. Hydrogen was H plus. It is gaining an electron, so its charge is compromised. Oxygen is losing its electron. That too, two electrons are required for one bond formation, right? Obviously one is its share only, for that it won't gain the charge, but for the second electron it is donating, for that it is going to have a positive charge. All right. Will oxonium act as an electron withdrawing group? Not an electron withdrawing group. It will be very unstable. It will gain stability by withdrawing electrons from the carbon oxygen bond. So yeah, once again, I'll give you a clarity on this step one. So in the step one, H plus is coming from the acid, and this H plus is electron deficient. It does not have any electrons to form a bond. That's the reason why it is attacking oxygen, which has surplus of electrons. In the process of bond OH bond formation over here, obviously two electrons will be required. Both the electrons are donated by the oxygen atom only. So what happens to the H plus, 1 unit of positive charge on the H plus ion initially? That will be transferred to oxygen because it is the one losing electron to the OH bond formation. That's why it ends up having a positive charge. That's the reason why it is oxonium ion. And coming to the second doubt, will oxonium acts as an electron withdrawing group? Definitely, oxygen is having a positive charge, right? It is an electron deficient. Here, there is electron deficiency on the more electronegative atom in the molecule. Obviously, it will be withdrawing the electron pair, resulting in carbocation formation. So, this oxonium ion to carbocation formation is the rate determining step. So, this will be our reaction intermediate, that is carbocation. Especially here we got tertiary carbocation. So in the second step we will be removing a H plus from the carbocation, so that we will end up having a particular alkene. So step 3 will be regeneration of H plus or removal of H plus, because we have to maintain a balance, right? So removal of H plus from beta carbon. So let's see what are all the beta carbons that we have. So 1, 2, 3, all of them are equivalent only. So let's say I'm writing CH2 and you have H over here. So this will be removed as H plus. Okay, this will be removed as H plus. If this is H plus, there will be lone pair coming onto this carbon, right, beta carbon, and that will end up a new pi bond formation, double bond CH2 and CH3. So this will be removed as H plus. Okay, so this bond pair will form a new pi bond over here, CH2 CH2. So this will be our alkene, 2 methyl prop 1-ene, 2 methyl prop 1-ene. Okay, so step 1, step 2, and step 3. First step will be forming an oxonium ion, which will be due to the attack of acid. This oxonium ion is very unstable due to the positive charge on the more electronegative atom. So the immediate step will be removal of this more electronegative, the withdrawal of this carbon oxygen bond, resulting in a carbocation. So the positive charge on the oxygen will be shifted to the carbon. giving us a carbocation, and the water molecule will be removed in this step itself. This is our rate determining step, the slow step. Now, since the carbocation is formed, and in the first step we have used H plus, this H plus has to be regenerated so that the reaction carries forward. For that reason, from the beta carbon, the H plus will be removed and a new pi bond between the initial alpha and beta carbons will be formed, and this H plus will be utilized to ionize the next alcohol, the other alcohol atoms. Okay, so this is the mechanism. Tertiary alcohol to having a substituted alkene as our product. All right. Isn't this also even elimination, but it has three steps? Yes, this is even elimination only, right? We are having carbocation formation. Why are we getting this extra step? Means because the attack of H plus is our initiating one, right? The attack of H plus ion onto our alcohol. That is our initiating step. Obviously, an extra step is required to show from where to where the electron shift is happening. All right. Okay. Uh, what happened? How much more is left to complete for this week? Is the rearrangement? If all, uh, how could you show which one is the? Yes, oxonium ion is the step one. How much more is left for this week? Only one more mechanism part. I told you there is one exception part, right? That exception part you have. Okay. I think someone, Muhammad Rahman, someone by my mistake you have on your video, it seems. Okay, please check. And you're lying on your bed. Okay, all right. One more mechanism. From there, we can finish this dehydration part actually. In case of rearrangement, if the alcohol, the number of steps increase, alcohol, yes, only one extra step just to show what is the attacking site for the H plus ion. Because in the previous case we used to remove the halide part as it is, right? If it was halogen, we used to remove the halide part as X minus. Here we are removing the OH part as H2O, which means we have to show at what site, what are the exact sites this H plus is attacking. So that's the reason why we are writing one extra step, nothing more than that. Okay, all right. So this is one thing. I told you that there is a little exception, right, when it comes to butane 1-ol. So let's see that exceptional mechanism, and from there we will see the generalization part. Oxonium ion formula, could you tell, is it RH2O plus? Definitely, oxygen with a positive charge is oxonium ion. Just like carbonium ion with carbon with positive charge, right? Carbonium or carbocation, we will call it. Carbonium is carbon with a positive charge. So oxonium is for oxygen with the positive charge. All right. Still any more doubts regarding this mechanism? And in case of rearrangement, okay, done. Chalo. Let's see the exceptional case where we had a rearrangement to give more stable alcohol. So take the starting material as butanol mud. Take down the next example, butane 1-ol. So we have CH3, CH2, 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 OH. So this is our primary alcohol. So let's see how exactly the rearrangement will happen. So we will be having rearrangement of primary alcohol. So let's start. In the step one, same attacking of H plus on the lone pair of alcohol group will be common. So you have H plus. Here also you'll have oxonium ion, CH3, CH2, 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 OH. Sorry, H you have oxygen with the positive charge, oxonium ion. In the second step will be, as usual, the removal of water molecule. CH3, CH2, 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 OH, H with a positive charge. We are removing water molecule. Now we end up having alcohol, sorry, carbocation. CH3, CH2, CH2, CH2 plus, right? So what is the type of carbocation we have? This carbon is attached to only one other carbon atom. So this is primary carbocation. Now, are there any possibilities other than primary carbon in the long chain? We have to cross check. So this is our secondary carbon. This is also our secondary carbon. So if there is any possibilities to get a more stable carbocation. So what is the stability order for carbocation? Tertiary more stable than secondary, more stable than primary. During the process of uh, this water removal, we are ending up with a primary carbocation, which is the least stable. This will not give us the major product. So we will be looking for chances in like by rearranging something. What are the molecules groups we will rearrange? I will tell, but we will be looking for another another or higher carbon, especially if you have primary, we will look for possibilities to get secondary or tertiary carbocation. Now in our given molecule, we definitely have secondary carbon available. So we will be performing a simple rearrangement called as Wagner rearrangement. Wagner rearrangement. So Wagner rearrangement. So what exactly is Wagner rearrangement? Means literal shifting of groups will happen, and those groups are mostly phenyl groups. Shifting of phenyl C6H5, that too with a negative charge, or hydride. Hydride in the sense hydrogen with a negative charge, or else we can even have methyl shift also, or methyl. Here also methyl group along with the negative charge we will shifting of either C6H5 minus or H minus or CH3 minus to form a more stable carbocation, to form a more stable carbocation, more stable carbocation. So this literal shifting of hydride or methyl or phenyl. Most commonly we will be encountering hydride shift or methyl shift. So in this butanol we will be seeing hydride shift only, and that too not between any random carbon atoms in the chain, specifically 1,2 shift. That is 1,2 hydride shift or 1,2 methyl shift if the group is CH3 minus, or it can be 1,2 phenyl shift. All these are Wagner rearrangement. Everything is to get a stable carbocation. So let's see what is the possibility for us in the given carbocation. So what do we have? Our carbocation CH3, CH2, CH2 with a positive charge. Always our carbon with a positive charge will be treated as number 1. Okay, and this is our hydrogen and this is our hydrogen. So in the carbon number 2, we have either ethyl group or 2 hydrogen atoms. So we will be performing on the second, like there is no ethylene shift, right? We only have methyl shift. Since there is no methyl group, we will go with the hydrogen. So this hydrogen, whatever we have in the second carbon atom, on the second carbon atom, it will be removed as H minus along with the electron pair. it will be removed. So we are performing rearrangement. 1 comma 2 hydride shift. So please concentrate how I'm writing uh, the shifting. Excuse me one second. CH3, CH2. So this is our CH, this is our CH2 initially. So what will happen? I told you that hydride shift will happen via H minus atom, sorry, H minus ion. So after the losing of this shared pi to the hydrogen atom, this carbon will ends up having a positive charge. Yes or no? And this hydride will be shifted onto this carbocation. So this will be converted into CH3. Now, what is the type of carbocation we have? This is a secondary carbocation, comparatively a better stable carbocation than the primary carbocation. So, I'll repeat the process again. After removing the water molecule from the oxonium ion, we ended up having a primary carbocation. So, when we have least stable carbocations, and if there is any possibility to go for higher stable one via rearrangement, that will definitely happen in alcohols. And the name for that rearrangement is called as Wagner rearrangement. Not all types of groups can be shifted. It has to be either phenyl group or hydride, hydrogen with negative charge, or methyl group with the negative charge. This can be shifted between the adjacent carbon atoms only, and not any two adjacent carbon atoms, the one with the positive charge and the next adjacent, the beta position one. That's the reason why it is particularly called as 1 comma 2 shift. By default, our number 1 will be the carbon with the positive charge, right? So to the first carbon, hydride, if there was any methyl substituent, definitely that methyl group would have been shifted. That part I will tell you in the next example. As far as this butanol, the carbocation, butane carbocation is concerned, we only have hydrogens available on the second position. So this hydrogen will be shifted as hydride. Hydride in the sense H minus. This bond pair will be withdrawn by the hydrogen itself, and that will be shifted onto the first carbon, and it will be converted into CH3. It is no longer a site for positive charge. The one which is losing its H minus, that is this position, will be our new carbocation. This is a secondary carbocation. Now, once we get this secondary carbocation, then by default, the next process will be removal of H plus will happen according to Saytzeff rule to get most substituted alkene. So the rearrangement part is clear, right? Does anyone have any doubts? Please let me know. I'll explain again. Here, to improve the stability of the cation, carbocation especially, we are performing a rearrangement, and not all types of groups can be shifted. It should be either hydride or methyl, or this phenyl is the least. You will see very less number of examples on this, but mostly it will be hydride shift or methyl shift. Okay, so this is step 2, where the primary carbocation is converted into secondary carbocation, which is a better stable one. Now in the step 3, the removal of this H plus will happen, so that we will end up having an alkene. So here we have removal of beta hydrogen to regenerate the H plus, which was initially our attacking reagent. So again, there are two possibilities here for this secondary carbocation. You have CH2, CH plus, and CH3. So this is our beta, and this is also our beta. Two beta hydrogens are available. So if the elimination will happen from beta 1 hydrogen, we have CH3, CH2 double bond, sorry, CH double bond, CH and CH3. You will get but 2ene. And if the elimination happens from beta 2 carbon, I mean this part of the beta carbon, we will have CH3, CH2, C H double bond CH2. This hydrogen will be eliminated. Minus H plus, minus H plus. So but 1-ene. Obviously, but2-ene will be the major product because of its more stability than but1-ene. Why? Because this is the most substituted alkene. So this part is clear, right? So butane 1-ol to but2-ene is facilitated by 1, 2 hydride shift. So this was the exception I made you to mark while writing the example. So this rearrangement will happen to give a more stable carbocation, thereby giving a more stable alkene, that is but2-ene. Otherwise, we will be expecting but1-ene, that is least substituted one, right? That's going to be our minor product, not of importance. Okay, so I'll wait a second, take this arrangement down, then I will give an example regarding the methyl shift 1, 2 methyl shift. Hmm. Step 3 once again, definitely. So when it comes to step 3, this is our carbocation, right? There are two beta hydrogens possible. This is our alpha carbon. The one with like this will be our alpha carbon. Carbon with the positive charge will be our alpha carbon now. Now what happens? There are two possibilities for the alkene formation. That is, the H plus can be removed from any one of the two beta carbon, either this beta carbon or this beta carbon. Generally, I used to write beta only, right? But right now, since there are two of them, I just number them. Beta 1 and beta 2 are nothing, just the different possible beta carbons with respect to carbon with the positive charge. All right. So there are two possibilities. This is beta carbon and this is beta carbon available to remove the H plus. So by removing the hydrogen from this beta 1 position, we end up having but2-ene. Why? Because if I write something like this, H, this will be removed as H plus, and this lone pair, whatever we have, will be donated for the pi bond formation here. That is for beta 1 elimination of H plus. Now, if we go for beta 2, the second possibility, this will be H2, right? And you have beta hydrogen, something like this. Now this will also be removed as H plus, and this lone pair can be, sorry, this pair of electrons can be shifted over here for the pi bond formation between carbon 1 and carbon 2. So two possibilities to get butenes, one butene and but2-ene, which is major product. But2-ene is the major product. We are just removing the H plasma and the electron pair, whatever you have between alpha carbon and beta carbon will be forming a new pi bond, resulting in alkene. All right. Okay. Step 3. So what is the exception here? What do we expect? Butane 1, all right. So CH3, CH2, CH2, CH2OH. So what do you expect? This is the H. So this H and this OH will be removed. And this is our only product. Like that, you will expect. You will expect this as the major and the only product in the reaction mixture. But end of the day, but2-ene is the major product. Which is not possible just by looking at the molecular formula. You have to go into specifics, then only you'll get to know that but2-ene is the major product. Got it? Why this was an exception? Because the expected product is not the major product. This is what we expect. But in reality, the most substituted alkene, that is but2-ene, will be the major product. All right. Now you will see an example for methylene shift 1, 2 methyl shift CH3 shift. something like that. Is anyone still writing? Do I need to wait a minute, or can we just move on? If you want to me to wait, let me know, or else I'll move on. Okay, let's see. For methylene sheet, you wrote very good. So let's start now. Take down a simple example. Not simple actually, but take down anyway. So take another example. CH3, 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 CHOH, and CH3. So this is 2 comma 2, sorry, 1, 2, 3, and 4. So you have 3 comma 3 dimethyl butane 2-ol. Okay, so this on treating with acid and on heating it, you will have two entirely different products. Same here also you'll see the exception. So you will have CH2 double bond C, CH3, CH, CH3, CH3 plus CH3, C, CH3, CH3 double bond CH3. So between these two, you can see the initial molecule is different, the methyl groups are different in the products. So between these two, this will be the major product and this will be the minor product. How come it formed? Let's see step by step. So let's start with the mechanism. Okay, so let's start with the attacking of H plus. What do we have? CH3, C, CH3, CH3, CH, CH3, OH, by the attacking of H plus. Okay, I'm directly removing the H2O. Okay, let's not do step by step. Anyway, you know, right, how H2O is going to be removed. We will end up what type of carbocation? C, CH3, CH3, CH with a positive charge, and CH3. So this is the carbocation part that we are going to end up. Why is this exception? Major product is more substituted one only, right? Yes, it is more substituted alkene only. Just check the position of the methyl groups. Initially, they were on the same carbon. In the major product, they are on the adjacent carbons. So how come the methylene groups got changed? How come the skeletal structure of the parent chain got altered? So that's what the exception here. Not the exception, the kind of rearrangement to give. Okay, you understood the structural difference. Here both the methyl groups are on the same third carbon, whereas here one methyl group is on second carbon, the other one is on the third carbon. So here also one is on second carbon, the other one is on the third carbon. The position of the methyl groups is different. What do you expect? We expect this is alpha carbon and this is the beta carbon. Between these two, we will be expecting a product. Yes or no? All right, let's see. I will tell you how this happens. Did you understand why it was an exception? There was a difference in the skeletal structure of the molecule when it was alcohol, and after it got converted into alkene. Wait, 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 wait. Yes, all right, chalo. I'm not going step by step. I have directly combined step 1 and step 2. I ended up having a carbocation. Now, let's concentrate on the rearrangement part. So, what is the carbocation over here? It is attached to two other carbon atoms, being a secondary carbocation. This is a secondary carbocation. Now, are there any possibilities by rearrangement carbocation in such a way that we can get a more stable carbocation? Obviously, we should look for tertiary carbocation because we are already one step extra, that is secondary. So this is primary carbon. So This cannot be included. Whereas here you have in the adjacent position a tertiary carbon. So some shift can be done, and that too there are available methyl groups on these tertiary carbon atoms. So here we are performing 1 comma 2, we are performing 1 comma 2 methyl shift to get a tertiary carbocation. So let's see how this 1 comma 2 methyl shift will give us. So this is our initial CH3, 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 CH and CH3. So this is carbon with the positive charge. So what will happen, just like hydrogen in the previous 1 comma 2 methyl shift, carbon with the positive charge will be our number 1 and the next adjacent will be our number 2. So you might be thinking, why are we not considering this methyl group as the carbon number 2? Because that's not going to give us a stable one. It will give us a second, a primary, sorry, it's not going to give a tertiary carbocation, which is the only stable carbocation than secondary. So simply there is a methyl group, a higher carbon available than secondary one. So what's the process? Same thing. Any one of these, there are 3 methyl groups available to us, right? Any one of them can be removed along with the bond pair, so that we will end up having positive charge on the carbon. So this is the skeletal structure initially, CH, CH3. Now, after this methyl group is removed as minus CH3, it will be shifted onto the carbon with the positive charge. So you have CH3. Now the positive charge on this carbon is compromised because of the CH3 minus, right? So this will end up having a positive charge. So let's see what type of carbocation is this. This is attached to 1, 2, 3. 3 other carbon atoms, making it a tertiary carbocation, which is a more stable carbocation than the previous one. So what is the mechanism here? You have available methyl group on the adjacent carbon, and that methyl group will be leaving along with the bond share, giving a positive charge to the carbon atom, and that methyl group along with the lone pair electrons will be added onto the initial carbon with the positive charged one. So the charges are compromised on this, and the adjacent one from where the methyl got shifted will end up having a positive charge, thereby giving a tertiary carbocation. Right now, from this, let us see the possible product. So we have CH3 positive charge, CH3, CH, CH3 and CH3, right? So how many beta carbons are there? This is our alpha carbon, this is our beta, this is also our beta, even this is also beta, but these two are equivalent, these and these are equivalent. So okay, I already named as B1. So this is B1 and this is B2. So by the removal of H plus, so minus removal of H plus from beta 1 carbon, I mean here, by removal of this H plus, we end up having CH3, CH3, double bond C, CH3 and CH3. So here I have removed the hydrogen from the beta 1 position. Now in the next possible arrangement, the same removal of H plus but from beta 2, means the terminal ones. So what is the possible product? CH2 double bond C, CH3, C, CH3, yeah, CH3. So this is the possible product. So which is the most substituted alkene? This is the most substituted alkene, right? So this will be our major product. This will be our major product. So 1, 2, 3, 4. So 2 comma 3 dimethyl but2ene will be our major product. Why is this an exception? Means by just by looking at the molecule, what is our initial molecule? CH3, 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 CH, CH2OH. So we will be thinking of removing this part, removal of this part, and to end up certain alkene. But here there is no, this is a tertiary carbocation, right? CH2. So we expect the product to be something like this: CH3, CH3, CH double bond CH2, which is nowhere in the formed products. So that is the exception here. This is what you expected product by the removal of water molecule H and OH from the adjacent carbon atoms. But that's not happening here. There will be rearrangement in such a way the intermediate formed, especially the carbocation formed, will attain a further stable carbocation state, and from there the Moses substituted alkene will be the major product. Okay, so I'll wait for a minute, I'll minimize the screen, you write down, and from there we will see one more example, and with that we can wind up. Actually, E2 mechanism also follows a rearrangement, but the course of the course of the mechanism will be a bit different. Instead of in between the mechanism, after the alkene is formed, the rearrangement will happen. So only that part I will try to cover in tomorrow's class, and we will revise so that it will be helpful for test. I'll wait a minute, note this down. We will see one more example if time permits, and from there we will move on. Yeah, this is a secondary alcohol. For primary alcohol also we can perform. This is secondary ROH. For primary alcohol we will see, and then we can wind up the class. Please let me know once you are done, okay? I'll wait. Can we say for the stability of carbocation, the rearrangement takes place and the rearrangement is for a tertiary carbocation? The first half is correct. The rearrangement will happen to get a stable carbocation, but need not to be a tertiary carbocation in each and every case. That part we have seen in the above case also, where a primary carbocation was the expected one, but through rearrangement we got a better one, a secondary one. So need not to be always a tertiary carbocation. It can be secondary also. Only thing is it should be a better one than we from what we are getting. Yes, definitely this entire rearrangement is to get a stable carbocation. That's it. But need not to be every time secondary only or tertiary only. Whatever the possibilities we have between the adjacent positions, with that we will move on. Okay. Yep, we will move forward. I'll give primary alcohol. This is a secondary alcohol, right? That's why we aimed to get a tertiary alcohol. Now we will see an example where from primary to secondary we will improve, we will upgrade the carbocation. So take down the next example. Propanol we will take 2 methyl CH3 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 CH2OH. So here the OH is attached to primary carbon atom. So this is a primary alcohol. So this is a primary alcohol. So again, in presence of an acid on heating, we will end up products that look something like this. CH3, CH, yeah, CH2, CH3, double bond, this is one, and CH2, double bond C, CH3, CH2, CH3. Obviously, this will be our major product. So let's see the mechanism involved. So not all steps required regarding the rearrangement part we will see. So what happens after the loss of this OH? We will end up a carbon with a positive charge over here. So CH3, 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 CH2 with a positive charge. So here this is our carbon number 1, carbon number 2, and this is our primary carbon atom. Yes or no? Whereas in the adjacent position we have a tertiary carbon available. So for that we will be performing 1 comma 2 methyl shift. So what happens after 1 comma 2 methyl shift? So this is our skeletal structure CH3 CH2. This methyl group will be shifted onto the carbon with the positive charge. So here it will get added, and since this carbon 2 is losing its share of electrons, it will end up having a positive charge. Now here we got tertiary carbocation from a primary carbocation. Here also we got much upgrade, like directly from primary to tertiary, we got a very stable carbocation. Now from here we will try to see what are the possible alkenes after the removal of H plus. So we are trying to remove the H plus, and how many beta carbons are available? Obviously 2. So this is beta 1 and this is beta 2, the adjacent carbons. So if we are removing the H plus from beta 1 carbon, you have CH2, double bond C, CH3, CH2, CH3. All right. Now, if you are removing the beta carbon from, sorry, beta carbon, that is from the second beta carbon, if you are removing the H plus, we have CH3, CH3, that is a new pi bond will form over here. Double bond, CH, CH3. So what is the more substituted alkene? Oh, sorry. Yeah. So this is the more substituted alkene. Here we have only 1 and 2. Here we have 3. 2 methyl groups and 1 ethyl group. So because of that reason, product number 2 will be our major product. So if we name it, we have 1, 2, 3, and 4. 2 methyl butene. So starting with propanol, 2 comma 2 dimethyl propanol, we ended up having 2 methyl butene. All this is due to 1 comma 2 methyl shift. So 2 comma 2 dimethyl propane 1 all to 2 methyl butene. So as you can see, the course of the reaction is completely changed. So this is the second one. So even this rearrangement is also possible in E2 mechanism as well, but that part we will try to see in tomorrow's class. But there is, I told you that I will give you order, right? That order we will write down and then we can wind up the class. I'll wait a minute, note this down. After that, let me know. I'll write the order. Today, no chemistry study hour, no multis physics study hour. Same time, 2:30 to 3:30. It's physics today. 2 days continuously. Because the faculty like are busy with the other PTMs and all, so 2 days at least. So that other batches won't get clashed. All right. Our PTM is tomorrow, right? Yes. On Friday we have PTM. They'll give the slots actually. They will be sent directly in the group. They'll give an Excel sheet. So based on the timing and all, you can come and get your PTM done. Most it is in the afternoon session, 2 to 5. Morning classes will go as usual. Study hours won't be there. So the PTM will be for 3 hours, 2 to 5. For us it will be 3 hours. For you guys it will be around 15 to 20 minutes, not more than that. Time slot will be allotted for each student. Yes, each student they'll give you the time slot actually. For each student, name by name, they'll give the time slot. So 3 hours, right? So 4 3 the 12. 12 students tomorrow, another 12 day I mean on Monday probably. Like give or take two more students, like 14 to 15 students in a day they'll arrange. Okay, chalo. Let's see the ease of dehydration, and after that, we can wind up the class. So, ease of dehydration, ease of dehydration of alcohols. Okay, there are three orders to consider. All those three orders we will try to take care. So, first thing is obviously to regular alcohols. Second, tertiary greater than, secondary greater than primary, because the more stable carbocation, if it is forming, the more is the reactivity. So tertiary greater than, secondary greater than primary. So small examples, same, CH3, CH3, CH3. So this is tertiary alcohol, which is greater than secondary CH3, CHOH, CH2, CH3. This is secondary alcohol because the carbon to which OH is attached is the secondary carbon. Then primary CH3, CH, CH3, CH2OH. So this is primary alcohol, and then you have straight chain CH3, CH2, CH2, CH2OH. This is also primary only, but oh, use the greater than symbols, not these. Now, this is also primary, this is also primary. Then what's the difference between this compound and this compound? The thing is, once the dehydration is done, this one will give a better branched alkene than this primary alcohol. That's why it is in the higher rank. Okay. So that is one thing. Even for cyclic compounds also, we can have actually there the stability and all. Okay, we did not see the cyclic groups, right? So let's say this is a cyclic alcohol, cyclohexanol, especially. So on treating with concentrated H2SO4 and on heating, so this is our alpha carbon, right? Alpha carbon. This is our beta, and at beta you have two hydrogens. Even here also at beta you have two hydrogens. So by removing water molecule, we end up having alkene from cyclohexanol to cyclohexene. This is also dehydration giving us alkene. So like this also we can have, need not to be every time open chain compounds only. Okay, so in the ring, if there is any conjugation in the sense alternating pi bonds, if there is any availability, there also we can have stability, the reactivity order. So OH with two altering bonds. So this is alpha. This is the position where we are going to get carbocation, right? So with that, we are trying to write the conjugation. So this is more reactive than this, which is more reactive than this. So what's the reason for stability? All these three are, or the initial two actually. These two are stabilized by extended conjugation. Why? You might be having a doubt with what they are having the conjugation with, in what with are they are in alternate position. After removal of the OH, you'll have a positive charge over here, right? So positive charge, sigma bond and a pi bond. Here also positive charge, sigma, pi, again sigma and again pi. So there is more conjugation in the first compound than second one and the one without any conjugation at all. So this is the ease of reactivity. So why are they reactive? Shouldn't they be more stable? Obviously, they are stable, but not in the molecular form once they form a carbocation as the reaction intermediate. Why is more stable carbocation that much important means? Because that's the one giving us the major product at the end of the reaction. So these two are stabilized by extended conjugation. Extended conjugation. Okay, so here the Hoffman product is very rare during dehydration. Most of the times, the major product will be SADZ, that is the most substituted alkene only. And in the first one, can phenol become? Yes, it will become a phenol, definitely. It will become a phenol. It will become a phenol. So here you can have a double bond, beta hydrogens over here. So a new pi bond can form over here. While in the carbocation stage, that carbocation will be stabilized because of the extended conjugation from the carbons of the other positions, definitely. All right. So in tomorrow's class, I will give a small E2 mechanism for the same rearrangement, because only all these are using carbocation only. We have never touched E2 mechanism where the base was directly interacting. Like everything was about carbocation formation only. So tomorrow we will see E2 mechanism, and I will cross check whether there are any important questions, important parts and all. We will try to discuss them. It will be like a revision for us.